Aloha, my name is Justin Fletcher and I'm a graduate student at the University of Hawaii at Manoa. Today I'm going to be sharing with you some work in deep optics for optomechanical control policy design here at WACV 2024. I'm going to begin with the motivating application for this work and then describe the approach we've taken to solve a problem within that application area. I will tell you about some experiments we performed and the conclusions that they've allowed us to reach. I'm going to begin with that motivating application, which is space domain awareness. Space domain awareness is the task of understanding what is happening in space, right? So these is mostly concerned with satellites near the Earth. We sometimes call these resident space objects, and we are interested in understanding how they're moving, where they are, what their state is, and we typically do this with large networks of small telescopes, but these telescopes usually cannot get us resolved imagery of the object like you see on the bottom left, and we really want resolved imagery because it gives us exquisite characterization information, tells us about the health and status of these satellites. So we're very interested in how we can do that. It typically requires large telescopes, and of course large telescopes are very expensive. So this is prohibitive for this application area, and we'd like to figure out a way to build large telescopes that are more affordable. Fortunately, we're not the only people with that goal. The exolife community also needs large telescopes for high contrast, high angular resolution imagery, and so we are going to, in this work, use just one of those designs called ELF, the exolife finder, as our representative telescope. This telescope improves the scaling properties of the aperture as the cost of the aperture as the telescope gets larger, but unfortunately introduces wavefront error because of the less rigid substructure that it employs. So we can compensate for this by making choices about how to actuate those mirrors or corrections with secondaries, but that requires a policy. We have to choose what it is we're going to do, what the system is going to do in order to maximize the desired objective for those images, whatever that is, whether that's image recovery or source separation or whatever that happens to be. So all these policies yield images, but how we use them matters. So how do we use the images that we form given a policy? So this really leads us to our central question. How is it that we can find useful actuation policies in image recovery algorithms? And these have to be jointly useful for ELF-like optomechanical systems. And so I'm going to describe now our approach, but I have to begin with a little bit of a diversion, because really, what does it mean for a policy to be useful? Here, when I say a policy, I'm talking about a thing that is making a choice about how to articulate a pupil function. And so here on this image, you see two pupil functions. They're sort of they're the second image from the right on top of each other. At the top is pristine. This is a perfectly flat pupil function. And on the bottom, there's some parameterized aberrated pupil function. That's what you're seeing here. And so what I'm illustrating with this, what I intend to illustrate with this image is that it's actually complicated how which decision you make about what your policy is going to do is not as simple as just minimize the errors. Because if you look here, what you're seeing is just minimizing the aberrations. It doesn't necessarily correspond to the most useful policy. I've taken a target here, and this is a simple imaging system where I have used the pristine pupil function to generate a strel of 1, a perfect strel PSF, and then convolve that with the image, and you get some MSE recovery for that target. But then this aberrated pupil function, I've actually deliberately adapted that pupil function to make it maximize the recovery of that specific image. And so obviously it's not the case that the most useful policy is one that minimizes aberration. So is it the one that maximizes object recovery? Well, not really, because it depends on which object you're talking about. In this case, I had the luxury of knowing what I was going to image in advance, the 1951 USAF target panel, and so I was able to choose that pupil function just for that one. But what if I have a broad class of images? What if I'm talking about the class of natural imagery or the class of non-resolved imagery for the XLF community, for instance? And so what we really need is a definition that includes both the context in which the task will be performed and the objective to which a task will be applied. And so we're going to say an actuation policy is useful when it improves task performance. Now, what I've done here is framed a problem that requires a solution both on the policy side and on the task model side, because the task model operates on policy. Think about this as if I make a bunch of decisions that are going to influence which images I'm going to produce, or the kinds of images, the sorts of noise patterns, for instance, that are going to be present in the images I produce, well, that means that the task model has to operate in the domain that is represented by those images. The task model operates on policy. And this means that those two things are reciprocally interdependent. So they have to be co-adapted and also adapted to the domain of application. And so finally, here's our approach. This is what we have chosen to do. Taking inspiration from the deep optics literature, what we have chosen to do is treat this dynamic optical system, this system that is able to control these mirrors, this pupil function of these mirrors, as the physical layer in a deep optics system. And of course, the task model is acting as the digital layer. And so what we've got is, starting from the left side, you have some object, which in this case is just an example image from the iNaturalist data set. And what you're doing is taking the power spectrum of that image and convolving it via the MTF process, convolving it, adding some noise to it, and producing an example image. And we're doing this in multiple sequences via some parameterized models that I'm going to describe in a second. And so our approach is to learn an articulation policy and a recovery algorithm end-to-end by propagating loss gradients through this differential parameterized model of ELF. So we're going to talk about that now. So this optical system proxy model is going to be very familiar to anybody who's done Fourier optics before. The image is the inverse Fourier transform of the modulation transfer function times the power spectrum of the object plus some noise. And of course, the MTF is generated from the pupil function. But what we've done that's a little bit different here is that we've parameterized that pupil function here by what we're calling a plan, and there's details of this all in the paper. And so that plan corresponds to a set of parameters that can be optimized that in turn correspond to commands we can give to a deformable mirror secondary that is, behind each one of these apertures to yield a set of images. And so we have a model, and then for our task model, we have a model function approximator that is parameterized by some parameters, theta r in this case, that produces an estimate of the underlying object, and then our task performance is measured by the expectation of the loss, the mean absolute error loss between the object and this recovery. And so our objective is to find these two parameterizations, theta p and theta r here, which parameterize the policy and the recovery task respectively, hence p and r. So we have a fairly standard model approach for this. We have a multi-scale feature abstractor concatenated with a feature fusion network as our model. This really isn't part of the research, but we've adapted it from someone doing something very similar. And we are minimizing this mean absolute error loss. We are going to measure our performance with 3 metrics, each one of which is normalized. Here we're using SM, PSNR, and MSE. Each one is normalized by the performance on the same metric of a monolithic aperture. D here, SMD for instance, is the SM of the distributed aperture system, the one that we can control, and that's normalized is divided by the SM performance of a monolithic aperture. The reason we did this is because, related back to our original application objective, which is to reduce the cost of extended object imagery, what we're really interested in is comparing how we perform with respect to a monolithic aperture of the same size, because if we perform equally well or better, and our design is much cheaper, then we can accomplish the original objective of extending the accessibility of resolved spatially extended object imagery. And of course, we need data sets to represent the domains in which we are applying this approach. So we've chosen Speed Plus, which is a data set of satellite imagery to represent the spatially extended space object imaging scenario, and then iNaturalist to serve as a much more challenging data set that also allows comparison to the broader body of deep learning literature. Our experiments are described next. I'm going to keep most of the description of these experiments in the paper, but I do want to just review our results very briefly with you. And so the first question we were really interested in asking is, can this optical system act as a feature extractor? Because that's very interesting if it can learn features that it implements via a control policy that improve overall task performance. Our experimental procedures are in the paper, but our conclusion was yes, in fact it can, and by increasing the actuation depth, you can actually get better performance on the overall task model, indicating that there are features that can be learned and produced from the control policy that the model alone, just the recovery model alone, cannot create. The major question in this work is, can we jointly learn control policy and recovery algorithms? And the answer is yes, and to a degree that exceeds the equivalent performance of monolithic aperture telescopes. And we have qualitative results that back those conclusions up, which are described here. And then finally, we want to know, does this approach generalize to large-scale tasks like iNaturalist, which are much, much more challenging? And the answer is yes, it does. We were able to, through multiple model sizes and multiple experimental parameters under both atmosphere and no atmosphere, we were able to achieve imaging parity with this system. We have some qualitative results to back that up, and of course, all of our results are in the paper. I thank you for your time and attention.